So again, we're looking at about a 2.5-week chapter on factoring, 3-week chapter on factoring. We're talking about factoring. If we look at what we did within the last unit of study, 7A, we talked about multiplying monomials times monomials and binomials times binomials. We talked about all those different types of multiplication that we can do. When we're talking about factoring, we're talking about going really in the opposite direction. How do we undo multiplication? How do we undo a multiplication of a monomial times a binomial? How do we undo if we multiply two binomials together? And that's what we call factoring. Today, we're going to look at two specific things. First thing we're going to talk about is we're going to talk about prime factorization and how you go about taking a number and writing it as a composite of prime numbers. That's called prime factorization. We're going to use what we call a factor tree. The second thing we're going to do then is we're going to use what we learned from prime factorization and those factor trees, and then use that to help us find what we call the greatest common factor within those two things. So 2 things to do today. How do we go about doing prime factorization? What does it mean to do prime factorization? And then how do we use what we've learned with prime factorization to do which is a much bigger topic in finding the greatest common factor. We're just going to look at numbers today when we do factorization and greatest common factor. Is everybody able to do the prime factorization and the greatest common factor?
I guess. Yeah.
We're all good?
Yeah.
All right. Your assignment for tonight. So first, some terminology. If we talk about something being prime, if we talk about numbers being prime, what do we mean? Does anybody remember what that means? Go ahead. A number that can be multiplied. You try to use division more a little bit. Something is prime. Can somebody give me an example of a prime number? 7. Okay, 7 is a number. 11 is a number. So somebody said you can't break down. What do you mean by can't break down?
You can't split it in half.
By 1 and itself. Okay, so we say a number is prime if its only factors are 1 and itself. So prime essentially means only factors are 1 and itself. Okay, so then there's another term in there that maybe we don't know what is. So if we say, okay, well, I've got another term in there, factors. I really don't know what factors are. What are factors? That you multiply together, that result is something. Okay? So they're the result of dividing a number. So we would say the factors of 12. The factors of 12 are 1 and 12, 1 in itself, 2 and 6, and 3 and 4. Those are the factors of 12. Factors are essentially numbers that you can divide out of a number that when you multiply them together, you get back to where you started. And we call those the different factors of 12. So the word that we were using that we wanted to be able to do today was what we called prime factorization. Where we kind of put the two words together. So when we're talking about prime factorization, what we're talking about is we're talking about taking any number and finding the factors of that number that the results are all prime. But when I multiplied all those numbers together, we come back to it. And that's what we call prime factorization. And what we use for prime factorization is we use what we call a factor tree. So So if I'm going to take 12, and I'm going to find the prime factorization of 12, I'm going to look for factors of 12. Well, we said the factors of 12 were 1 and 12 and 2 and 6. I'm just going to pick 2 of them. Doesn't matter which one I pick, and I'm going to branch it off. And I'm going to pick 2 and 6. Now, one of those numbers is prime. 2 is a prime number. It's only divisible by 1 and itself. 6 isn't a prime number. So since 6 isn't a prime number, I need to factor that 6 even more so that it's the product of 2 primes. So 6 is 2 and 3. And 2 is a prime number, so I'm going to circle it. And 3 is a prime number, so I'm going to circle it as well. So now I can't break down 2 because it's prime. I can't break down the other 2 because it's prime. And I can't break down the 3 because it's prime. So I can rewrite this in what we call expanded form. Expanded form is just taking all of the numbers that I have circled and writing them down and multiplying them all together. And if I do this, 2 times 2 is 4. 4 times 3 is 12. I get back to my original number. That's called expanded form. That's one way to write them. Another way to write them, and the preferred way to write them, is to write them in exponential form. And we've done this before. How many 2's do I have? 2. So 2 squared is the same thing as 2 times 2. So I can rewrite the 2 times 2 as 2 squared times 3. These two things mean exactly the same thing. It's just 2 different ways to write it. We are going to use that as our preferred way to do it. Well, the question then that gets asked then is, all right, we had all of these factors of 12. We had 1 and 12, we had 2 and 6, we had 3 and 4. Obviously, if I do a prime factorization tree, I'm never going to pick 1 and the number. It just doesn't make sense because I'm back to where I am. But what happens if I would have chosen 3 and 4 instead, and I didn't use 2 and 6? Well, if you notice, the 3 is still prime. 4 isn't. 4 I have to break down into 2 times 2. 2 and 2 is prime. All of my things are now circled. So this becomes 2 times 2 times 3, which is 2 squared times 3, which is exactly the same thing as I had before. And that's okay. And that's what should happen. Key to this is it doesn't matter which way you choose to factor it. You will get to the same answer eventually if you've done everything correctly. And that's kind of the key. Okay. Let's look at another one. Let's look at the prime factorization of 30. And we're going to do the prime factorization of this. Okay, I'm not going to list all the factors of 30, but I'm just going to think in my head. What times what? 5 times 6. Does 3 times 10 work? Does 2 times 15 work? Yes, they all work. I chose 5 times 6. It doesn't matter. But I'm going to circle the prime number. If you go up into that cupboard, open it up, there should be some napkins. Right on top. 6 isn't prime, so I'm not going to circle it. Factors of 6, 2 and 3. Circle, circle. I have a 2, I have a 3, and I have a 5. That's all I have. That's the way this needs to be written. It's not 2 squared. There's only one of each of them. You don't have to put it. And you never have to put a 1. 1 is kind of always understood to be there. Let's go ahead and try 80. Let's find the prime factorization of 80. Go ahead. See if you can get it, and then write it in both expanded form and then exponential form. Oops. So factors of 80. 8 and 10. If you didn't use 8 and 10, just do what you did. That's fine. Either of those are prime. Break down 8. 2 times 4. The 2 is prime. Now, I just keep going. Once I've branched off, I finish this branch. So this is 2 times 2. And then 10 is going to be 2 times 5. And again, I'm just circling because I know they're prime now and I can't break them down. So it's 2 times 2 times 2 times 2 times 5. How many 2's do I have? So it's 2 to the 4th times 5. And you're done. Any questions with that one? Go ahead and try 300. Do the prime factorization for 300. Ladies, put the phones away and let's do the work. Right, so how do we want to start 300? 3 times 100? 3 is prime. What are the factors of 100 that I could use? What? 10 times 10? 2 times 50? There's lots of them. 2 and 10 is probably a good one because I know that they're both going to be the same, right? So I've got 2 times 2 times 3 times 5 times 5. So 2 squared times 3 times 5 squared.
That's what I got.
Good. So are we okay with the prime factorization piece of it? And we'll get more practice here in just a minute if you're not.
No, we get it. We get it.
Okay? So now the second part that we said that we needed to talk about was we needed to talk about what we call the greatest common factor. Or the GCF. Now that greatest common factor, by definition, it's pretty self-explanatory. It's the greatest number and variable that the numbers that you are given have in common. And it can be 2, it can be 3, it can be 10 numbers that you're given. But we want to find the greatest common factor for them. So if I take something, let's say that we want to find the GCF of these two numbers, 30 and 50. Well, one of the ways that you can do this is you can do exactly what we've been doing. You can use the factor tree. So since we've been practicing the factor tree, let's just do this using the factor tree. So 30 was 3 times 10. 3 is prime. 10 is 2 times 5. So I'm just going to write it as 2 times 3 times 5. Now we're going to do the same exact thing for 50. It's 5 times 10. 10 is 2 times 5. So that's 2 times 5 times 5, which is 2 times 5 squared. Now when we're looking for the greatest common factor, we're looking for numbers that they have in common. And we're going to take those numbers that they have in common and we're going to multiply them together. So sometimes it's easier just to leave it in expanded form, sometimes, to do this. If we look at common, they have a 2 in common. So part of my GCF is going to be 2. The other thing they have in common is the 5. So they've got a 2 and a 5 in common. To find the greatest common factor, you multiply those two things that they have in common together. And 2 times 5 is 10. And that's our greatest common factor for 30 and 50. That's one way to do it. In all honesty, mathematically, it works great. If you're good with math facts, if you're good with number sense, which some of you are, some of you aren't, some of you honestly could just look at this and say it's 10. Great. If you're a person that can do that, more power to you, because that's going to help you down the line. Because we're going to do this a lot.
Especially in algebra 2.
Well, and especially in next week or tomorrow. Tomorrow. The other way to do it is you could sit here and list all of the factors of 30. 1 and 30, 2 and 15, 3 and 10. Those are the factors of 30. You could also do that for 50. 1 and 50, 2 and 25, 5 and 10. What's the biggest one that they have in common? 10. So there's different ways to do this. We're going to kind of concentrate on using the factor tree and prime factorization to do these. So let's look at another example. Let's go with 66 and 90. We are going to find the greatest common factor for 66 and 90. Let's go. So 66. 3 and 22. 3 is prime. 22 is 2 and 11. So it's 2 times 3 times 11. 90. 3 and 30. 30 is 3 and 10. 10 is 2 and 5. So that's 2 times 3 times 3 times 5. So we look the ones that they have in common. They've got a 2, and they have a 3. 2 times 3 is 6. So that's our greatest common factor for those two numbers. Well, we said it doesn't just have to be two numbers. It can be three numbers. So for the next one, let's go with 64, 48, and 80. So now we have three numbers involved. How you do it doesn't change. You do the factor trees for 64, you do the prime factorization tree for 48, and you do the prime factorization tree for 80. So why don't you go ahead and do those three prime factorization trees and then stop. And then we'll put the GCF together.
I literally got all these ready. Chill out. So I did it. Bro, I did.
All right, so just to peek up quick, see how you did with your prime factorization trees. So 64 I have is 2 to the 6th. Just wait. Yeah. 48 is 2 to the 4th times 3, and 80 is 2 to the 4th times 5. Questions with that? Okay, so here's why it's nice to put them in this form. What number do they all have? What base do they all have the same? 2. So we know 2 is going to be there because that base is there for all of them. Now, because it's 2 to the 6th, 2 to the 4th, and 2 to the 4th. So we have a base of 2. Now, when you have bases are the same that are risen to exponents, the amount that they have in common is the smallest exponent that you have for any of them. So what's the smallest exponent we have for any of them? 4th. So 2 to the 4th is going to be our greatest common factor. Remember, 2 to the 4th is 2 times 2 times 2 times 2, which is 16. That's your greatest common factor. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And if you look up it from above, 2 There's 1 in each. There's 2 in each. There's 3 and 4. There's 3 and 4. There's 3 and 4. They don't have 5s or 3s all in common, so we can't put that 5 and 3 in there. Yes, you need to write it out as 16. Don't leave it as 2 to the 4th. If you wanted to do that on your calculator, remember on your calculator, you hit the 2, the caret symbol, and the 4 to do that. Okay. Any questions with that one? All right, let's look at the next one. Next one. Let's go 156, 52, and 130. Now go ahead and take this one all the way to the end and find the greatest common factor of those 3 numbers. Give you about 2-ish minutes. So there's the factor trees. So we've got 2 squared times 3 times 13. We've got 2 squared times 3 times 13. Oops, that's not right. Oh, 2 squared times 3 times 13. And then the last one is 2 times 5 times 13. So the first base that they have in common is 2, right? What's the smallest exponent?
2.
Just
Oh, just 1, yeah.
Just 1, right? This one only has 1. So they only have 1 in common. Do they have 3 in common? Nope. Do they have 13 in common? Yep. So they've got the 13 sitting there. So 2 times 13 is 26. That's your GCF. Okay. Any questions with that one? Okay, one more. Let's go 8, 27, and 50. We want to find the greatest common factor for those 3. Okay, take a peek up at the prime factorization trees because I know there's a question now. You know what? First person never gets caught. You should know that by now. So do they have any bases in common that all 3 of them have them? No. So what's the answer? 1. Very good. Everything has a common factor of 1. Everything has a common factor of 1. If they have nothing larger than 1 as a common factor, you put 1 as the greatest common factor. Do not put they don't have 1. All sets of numbers have a common factor. That common factor is always 1. Okay? It might be the greatest, it might not. You have to list it. That's going to come in big later when we start factoring by what we call factoring by grouping. So you have to take out a 1. So that's going to become important later on that you understand that fact. Okay? So we had two things.